Hello everyone. Hope all of you are well. I want to thank Black Hat for giving me this opportunity to present my tool. So today I would be talking about my tool called DarkWidow, which is actually a dropper slash post exploitation tool targeting Windows. Little bit of a background about me. I am Shomal Biswas. I currently work as a junior security analyst at Fire Compass. My daily work includes OSINT, malware and ransomware development and research, software development, source code analysis, attack vector simulation on on-prem and cloud environment like AWS. I have a little bit of a Linux kernel background because I once built a rootkit based on that particular area. I have interest in Windows internals, currently in user mode. Slowly, I am moving towards the seed, that is the kernel. Red teaming, I am CRTB certified. Recently started a bit of threat hunting for developing a knowledge of building detection scripts. I'm a very big fan of Batman as well as MMA. And I also want to thank Farhan Siddiqui, who is actually my co-worker, for helping me to build the slides. So the agenda for today is Windows internals, user land versus kernel land, EDR hooks, and bypassing strategies of that. Syscall introduction, then direct system call, indirect system call, introduction to my tool, then some internals about that. Then I would show you the demo, then another new topic, which is synthetic frame thread stack spoofing. Then based on that, I would show you the demo of version 2 of my tool, then future upgrades regarding my tool. So let's jump to the user land versus kernel land. So whenever we actually call a Win API, in this case the Win API is called create file. So it originates from kernel 32, then goes through NTDLL, and the Win API resolves down to integrate file into API. Then it calls the system call, and that enters the kernel. This is actually the main flow. So what EDR actually does is it actually targets the int API, and then it actually adds a jump instruction. Then after adding the jump instruction, the flow continues to this edr.dll. Then the edr.dll checks whether it is malicious or not. If it is not, then it's moved to the int API, then it continues to work as expected. But if it is malicious, it actually terminates that particular process. So when we see this particular area under debugger, we can see that this is called stub, and this 18 thing is actually the SSN number, and in this case this particular NT API isn't hooked, and when this NT API or syscall is actually hooked, you can see a jump instruction, and this particular address is the address of the EDR DLL. Yeah. So there are some of the techniques to get around this API hooking thing. The first technique is NT API unhooking, which actually involves loading of another fresh copy of NTDLL or only the text section of it in the process memory. So that's the thing. Then repatching the EDR patch, that is counter patch to the EDR patch is done to evade API hooking. Then manual mapping, that is manually loading a target DLL module or library, which is also called proxy DLL, in order to evade ETWTI or kernel callbacks. Then the fourth one, which is the overload mapping, module stomping, and module overloading, which is loading legit DLL into the process and overwriting its text section with our shellcode or PU payload. It is basically done because in this case we don't have to allocate RX memory region because DLL already have a allocated executable page. This is very much useful to evade EDR based memory scans. The fifth one is actually the syscall usage to bypass API hooking. This is actually a capability present in my DarkWidow. I actually use the indirect syscall one. So for that reason, the capability 1 and capability 2 is not needed because all of them basically serve the same thing, API hooking evasion. And the sixth one, the final one, is thread stack spoofing. It is basically done to evade call stack based detection stack monitoring via EWTI, and this capability basically present in the version 2 of my tool called DarkWidow. So syscalls are basically exported from the ntdll.dll. There are two types, nt and zw. The nt system calls are basically used in the user mode, and the zw are basically used for device driver development, that is present in the kernel mode. Yeah. So you can see these are all the syscall stubs, and you can see these are the SSN BA, BB, BC, BD. So you can see that syscall numbers are incrementing by 1. So we would be employing this technique, SSN plus 1, this particular algorithm, to retrieve SSN dynamically in runtime in our tool. So this is actually the WinAPI flow. So when malware calls a WinAPI, it calls a virtual alloc, which actually reside in kernel32.dll. Then it goes through kernel-base.dll. Then that particular WinAPI get resolved down to NT-allocate virtual memory, NT-API version of this WinAPI. Then if EDR is present and it is hooking it, then the control flow would move to EDR, that is hooking DLL. Then it checks whether it is malicious or not. The same thing which we talked about earlier. If it is malicious, then it would terminate. If it is not, then it would return back to the same NT API. Then it would call system call and do its own stuff. So here comes the direct system call. So what it actually does is it directly enters, you can see, the kernel. It doesn't involve kernel 32, kernel base, or NTDLL. So if that in particular NT API, meaning the integrate file W is actually hooked by EDR, so it wouldn't actually disrupt the malware.exe's task because it is directly entering the kernel, and in this way it is actually evading user mode ring 3 hooks. That is it. So there are two types of direct system call, static as well as dynamic. The static meaning the static or hard-coded system call, and this assembly procedure is actually used. This is actually shows us the system call stub that we are actually hard coding in the malware.exe process. And for direct dynamic syscalls, we would be retrieving syscalls dynamically at runtime. Here. So there are some of the extraction methods of the different extraction methods of dynamically extracting syscalls. So first one is actually the health gate, which actually retrieves syscall dynamically, but it doesn't actually checks the presence of hooks, that is the jump instruction. So in that case, it would fall short. Next comes the hellos gate, which is the modified form of health gate. Just it adds one thing, that it first checks whether the first instruction is a jump or not. If yes, what it does is, you can see it is a jump instruction. What it does is it checks the neighboring syscall. The neighboring syscall is ZW query value key and the ZW query information process. So what it does is it checks the neighboring syscall and checks whether there is a jump instruction or not. In this case, it is not there. It is not there. So then it would actually retrieve the SSN. In this case 17, in this case 18, not 18, 19. So what it would do is 17 plus 1, it becomes 18, this one, and 19 minus 1 is equal to 18. So SSN number of ZW allocate virtual memory will be 18. So in this way, SSNs are actually retrieved or calculated. The third one is the Tartarus gate, the modified form of hellos gate, where it actually checks whether the first or third instruction, which is the upgradation of a hellos gate, is a jump or not. So, and the last one, the modified Tartarus gate, checking diversified userland hooks to actually evade various type of AVs and EDRs. So what it actually does is, only this is actually the upgradation. The first, third, 8th, 10th or 12th instructions are actually checked for jump instruction. So it is actually done to see or evade much more diversified EDRs, because more EDRs, the meaning more diversified way of hooking APIs. and this would actually evade that particular thing, all those different types of hooks. And this particular method is actually present in my tool, but in indirect system call implementation. Yeah. There are some drawbacks of direct system call. This is the static one. We can see that with obj dump, we can directly dump all the system call stub in here, and presence of system call stub within a process memory is basically an IOC, and we can see that it is actually creating an IOC. And another thing which we talked about earlier, that it is rupturing the normal API flow, the normal API kernel 32, kernel base, NTDLL, then kernel mode. But in this case, it is directly entering the kernel, which is an IOC, and it would be actually be detected by a concept called instrumentation callback, or technique called instrumentation callback, aka Nirvana. And this is actually the demo of detection of direct calls, direct system call, so via instrumentation callback on Nirvana. So basically, see, I'm actually injecting the instrumentation callback detection DLL into my target process. You can see it is loaded. Yeah, SSN retrieve, then it is telling us kernel returns to unverified module and terminating. So this is the thing. So now we would jump to indirect system call. Why? Because indirect system call actually eradicates this issue, and I would be focusing on a dynamic version of indirect system call. So why it would be eradicating this issue? Because as it is directly entering the kernel, the direct system call one, it is getting detected by instrumentation callback. But in this case, the it will not directly actually go to kernel. So it would actually jump to NTDLL, then execute the system call, then it would jump to kernel. So, and that is the reason why it is not actually getting detected. So this is actually the system call stub. So here you can see SSN are actually retrieved, then it would jump to the syscall address, meaning the syscall address is present within the NTDLL memory. So that is it. And this is how the SSNs and syscall address are actually used within the assembly procedure. So here comes my tool called DarkWidow, and the capabilities my DarkWidow tool possesses are indirect dynamic syscall usage, SSN plus syscall address sorting by a modified Tartarus guest approach, remote process injection via APC early bird to cut off EDR telemetry catching by EDR, spawns a sacrificial process as a target process, not actually disrupting already open process in the environment, SEG and block DLL mitigation policy on spawn process, PPID spoofing, API and DLL resolving from TIB, TEB, PEB, then resolves NT API, then cursed NT APIs are actually hashed. So the capability 1 and capability 2. So in this way the SSNs are actually retrieved, and this is the way SSN addresses. So you can see these are the hook checks of 1, 1st, 3rd, 8th, 10th and the 12th instructions are actually checked with our E9, meaning jump instruction. If it is not, then okay. If it is, then it actually performs this algorithm to actually extract system call. Then the second picture actually shows how it actually extracts the SSN address. So now this again the same procedure, get syscall address, and this is the indirect system call calling stub. So what actually happens is the previous one, this is the one, this is the actually sorts SSN, and this is one which actually sorts SSN address. So here it sorts the sort SSN, actually sorts the SSN, that is the system call or syscall, and the get system call instruction actually sorts the syscall address. And after sorting SSN and syscall address, it actually calls get syscall and get syscall address, then get syscall address and get syscall and syscall address actually stores system SSN, system call, and syscall address within these particular variables. Then those variables are actually used to perform indirect system call. Then we are actually calling the APIs. This is how the indirect dynamic syscall is working. So now this is how the call stack looks. You can see the call stack looks totally legitimate. This is the normal CMD process. This is the implant process. So you can see here. So now the third capability, remote process injection by IPC early bird. So I actually used a particular NT API called NTQ APC thread. So I recently found a blog by Elastic where it says the Q user APC call stack not always available due to ETW limitation. So that means usage of this particular API would be beneficial for us in from evasion point of view. So the capability 4, which is actually spawning a sacrificial process of the target process, you can see we are actually create process A using this Windows API to spawn our sacrificial target process. And the sacrificial target process is actually security, health, history. You can actually spawn whatever you want. So I am actually adding ACG and block table capabilities into the spawn process as well as the PPID spoofing. So the block DLL capabilities are actually used because if the EDR DLL is not signed by Microsoft certificate, it would actually block that EDR.dll to be injected into my particular process, spawn process. If the EDR DLL is signed, then this thing wouldn't work. But if it is not, then block DLL would be helpful to defend our malware. And then it is performing PPID spoofing. So this is how it looks. PPID 8464, you can see 8464 and 23036, 23036, SEG and CIG are actually applied. So now the DLL and API resolving from TIB. So rather than directly accessing the PEB via GS60H, what I am doing is we are actually retrieving the address of PEB indirectly via TEB, GS30H. You can see here. Why? This indirect thing would actually help us to evade some of the EDRs as it is not accessing the PEB directly. So for that, we would be targeting a special structure called load order module list, where all the loaded modules are present in order. They are actually loaded in the process. Yeah. And this particular code snippet actually shows us that how we would be actually resolving NTDLL address from already loaded NTDLL from our present process, this particular thing. And this particular snippet actually shows us the how we are actually resolving int API dynamically. So in here, this line, we are extracting the int API function name. Then after extracting that, we are hashing that int API function name and checking with the hard-coded provided hash. I will be showing you where I kept the hard-coded provided hash. And after checking that, if it is equal, then it says that the hashes are matched and calculated, then it actually resolves that particular int API. So here is the hashing algorithm, which is very well known, the DJB2 hash. And this particular snippet actually shows that how we are actually calling the resolve DLL, which is actually resolve the NTDLL, which is the hard-coded hash. And this is the resolve NT API. This is actually the hard-coded hash of the NT API. So these hard-coded hashes are actually used to compare in here. So now extra capability. If we get an admin privilege, it kills the responsible event logging HVC host. You can see elevated debug AC debug privilege is disabled, and what it does is it actually uses AC debug privilege and enables and kills all the threads. Show you the demo. See, fast forward a bit. See, our process are actually loaded. No detection. See, no detection. See here, first forwarding a bit. Detection. Again, nothing. So yeah, no detection, no notification. So what are the event logs that are generated? No critical alerts are generated, but one low severity one, which is the asynchronous procedure call. I would be showing you how I eradicated this issue within a couple of slides. So now let me show you how it performed against the Sophos, but under admin privilege. You can see here, it is trying to kill. If it is not, then it is proceeding towards post exploitation. Yeah. See, bit. Yeah. EMI. You can see no notification, nothing. Hitting, no notification. So total evasion. So in this case, some event logs are actually created, which is the first one is the same as the asynchronous procedure call, which is the low severity, and the second one is the medium severity, which is actually showing a user account was changed. Subject logon ID 0x3E7. So which actually corresponds to the usage of AC debug privilege. So we got successful execution of our implant, but these logs are not like these logs are actually creating automatic suspicion. So we have to get around that. To get around that, please welcome synthetic frame thread stack spoofing. So with the synthetic frame thread stack spoofing would enable us to bypass call stack monitoring. So without call stack monitoring or stack obfuscation, this is how the stack would look like. You can see when we are calling get host by name and tp wait for wait, you can see it the call stack points back to its location, which is actually revealing a leak stack value, and this would be immediate suspicion if EDR utilizing ETW tracing checks the whole thread. So that would be an issue. So in our case, what we would do is we would be using stack spoofing to hide the source of our malicious NT APIs. So for if we see a legitimate process, we can see that the first two frames are kernel based. The first one is the RTL user thread start, and the second one is the base thread init thumb. So what we would do is we would create two fake frames like this and add it to the top of the stack. So now the int APIs would look like this. You can see totally legitimate, and the shellcode set tracks is looking like this. It's legitimate. And for shellcode development, I used Havoc, and this is actually the configuration. I used stack duplication here. Let me show you the demo. Show you. Yeah, you can see here that the first initial legit looking fake custom thread stack frame is created, then the second one is created, then the job gadget, then actually spawning particular sacrificial process. Show you this thing. You can see runtime broker is actually created, and yeah, no detection, no alert, no notification, no new notification. It is a bit small, but I would be showing you. See. Who am I? I will paste that in a notepad and show you. You can see here, right? Who am I? Then I would be performing service enumeration. Be copying this and pasting it again in notepad. You can see the Sophos file scanner is running. Sophos live query service is running. Yeah. Then also it is not getting detected. No notification again. So yeah, that's the thing. So with this, no logs are getting generated. And also I actually removed the event logging logger killing part, which is actually using AC debug privilege, which is actually creating a medium alert. So without the usage of that, then also we got total evasion. Also the event log is not created in this case. So this is my project link, my GitHub repo. If anybody who is actually seeing this, interested this, please contribute to my repo. I would be very much happy. So some of the future updates, I wanna port this version to C++ client compiler, which would help us to perform LLVM obfuscation. Then upgrading to integrate user process to perform indirect system call and stack spoofing. Then actually applying manual loading library capability to bypass image load kernel callbacks. Then applying module stomping. Then usage of encrypted shellcode injection to avoid kernel triggered memory scan. That is actually Karokan. So, and this is actually the Thanksgiving time. I actually want to thank all of them, those who helped me to build this project slash tool. Peter Wintersmith, Bobby Cook, Glaze Virus, Shomodeep Basu, John Mai, Shockefar, Sector 7, Virtual Alog, Dylan Fran, Jake Hallon, Dark Matter, and Winter Knife. Thank you to all of you for helping me to build this tool. And thanks. And yeah, that's it from my side.